present. There we go. Now, whatever you say will finish in YouTube. No, I'm kidding. So welcome. If you're joining now to this webinar, more people signing in. This is really cool. Thank you so much for joining. We are going to start in about 2 minutes with the first presentation. This is Switzerland, so we like to always be very right at the minute of 4 p.m. Central Europe time. And that will be in about 2 seconds. There we go. It is 4 p.m. in Switzerland. It is what, 8 a.m. in Colorado, I think. Yes, there we go. It's 8 a.m. in Colorado. And welcome to the Cloud Native Computing Switzerland Meetup. It is February 24th, 2022. My name is Adrian Kosmaczewski, and I welcome you from the city of Zurich in Switzerland. And this is yet another edition online of the Cloud Native Computing Switzerland Meetup. I know we planned to do this one in person, but the situation it is what it is. So we decided to go back to online, and I think you don't mind. I think it will be, in any case, a fantastic event we have today. So I'm really thrilled to welcome our speakers. And by the way, speaking about which, a little bit about the agenda for today. We are going to start with Moritz Eckert from Edgeless Systems GmbH from Germany, talking about confidential computing with project MarbleRun. So this is Moritz who will start today. Then we have Melissa McKay from JFrog, directly from Colorado in the United States. And this is one of the first time, I think it's the first time we have a speaker from overseas on this event. So it's really cool. Welcome, Melissa. She's going to talk about Distroless Docker images, and that will happen at 16:45 CET. And we are going to end this event with none other than Thomas Graf, CTO of Isovalent. He's going to talk about Cilium and eBPF, the hottest new technology in town. So it's really cool. Thank you so much for all of you to being here. And we're going to end around 18:05, which is more or less in about 2 hours. So just a quick reminder, this is being recorded as we speak. So basically, the video will be later available on our YouTube channel on vision.tv. So please subscribe for updates. We publish new content there very often. There's a Q&A box right at the bottom of your screen. So please use it. Please post your questions to your speakers. Each one of the speakers will basically decide whether to answer the questions live at the same time or asynchronously at the end, and so on. So basically, it's up to you guys to decide how do you want to handle this. But of course, everyone, please abide by the conference code of conduct. We never had an issue with this. The Swiss community is fantastic, very respectful. But there you go. You can read it on vision.ch. We've got the code of conduct. We are running a DevOps in Switzerland survey right now until the end of March. We are basically very curious, and we've got a very nice amount of answers so far about how companies in Switzerland are adopting DevOps. So please use your QR code. Please log in to the SurveyMonkey survey that is on the screen right now. And why I'm saying this, because there's a possibility for you, but you have to be located in Switzerland. Sorry, Melissa, sorry, Moritz, about that. But you have to be in Switzerland, because you can win one of two prizes worth 200 Swiss francs each. One of them being a voucher for Apuyo Cloud, which is our newest container platform based on OpenShift 4 that we just released a couple of months ago. So please, thanks for providing us with your information, and you have the possibility of winning one of these two vouchers. The other one is a voucher for Digitech, which is one of the big e-commerce websites in Switzerland, so you can buy whichever device you would like to have for your birthday. We've got more editions of the CNC Meetup planned for this year. We've got May, August, and November planned. We still have 2 slots available for May, so we already have a speaker for May. If you are interested to speak in any of these events, please contact us on cnc-meetup.ch. This is a URL that takes you directly to the vision.ch website with a form. The only thing we need to know if you would like to speak at our event is basically who you are, what would you like to talk about, and that's it. That's basically all the information we need. I will close very quickly. Please follow us on YouTube, because we have vision.tv. Follow us on Twitter, on GitHub, on LinkedIn, on Facebook, on Instagram, whatever you want. Please follow us. It's really, really cool. We are publishing very cool information all the time. So thank you so much. Enjoy the presentation. Remember to fill the survey if you can. And if you have time, it only takes 5 minutes. Believe me, it's very, very short. And go back to the agenda today. We're going to start now with Moritz. I'm going to unshare my screen. The screen is yours. And there we go.
Thank you, Adrian. Very great introduction. Very powerful. I like it. All right. Yeah, hi. I'm going to give you an introduction into how we bring together confidential computing and Kubernetes, and especially with our project MarbleRun. I guess most of you will be familiar with the term Kubernetes and all this cloud native stuff. So I'll take a bit of time and explain the concept of confidential computing so you know what I'm talking about. So the world as we see it, or the cloud as we see it, is a very dangerous place. There are a lot of components, people, parties you have to trust. There are so many potential threats and malicious actors. And if you transfer your workloads, your data to the cloud, you essentially give up the protection of your on-prem physical separation and expose your data to this world. And the general idea of confidential computing is that you can create a safe space in the cloud that you can securely communicate with and interact with, and thereby protect all your data and workloads in the cloud. And this sounds very promising, and of course, people are very excited about the possibilities of the new types of applications you can essentially build with this, and all those additional security and privacy protections you can build with this technology. And there are already some examples of existing solutions that use confidential computing. Two of the probably most prominent ones are the Signal content discovery. So the idea is that Signal can tell you who of your contacts is already using Signal without revealing your contacts to Signal or to any other party, or like transferring the contacts to a cloud instance where a potential malicious actor could steal them. So your contacts stay with you, and they can offer the service. And on the other hand, the e-Rezept, which is the German e-prescription service that's currently being built and rolled out. There's a talk from someone at the company that builds this service at a conference we did last week called the Open Confidential Computing Conference, OC3. I will have a link to that on the last slide. So we're also going to upload those talks to YouTube if you're interested in this kind of stuff. I'll point you to that. It's a very very interesting, ambitious project there. And confidential computing is not something that just exists in theory. It's something that the cloud providers are actively investing in.
Sorry, Moritz. Sorry, Moritz, to interrupt you. I don't think you're sharing your slides.
I don't share my slides.
I don't think you're sharing your screen.
Try again. Is it back?
And now we can see your screen. Yes. Thank you so much.
Didn't you see the screen the whole time?
We only saw you, yes, from the beginning.
Oh, okay. Oh, that's not too bad, I guess. I can show you the nice graphics I had about the
exactly as one of the
secure cloud environment.
Absolutely, as one of the attendees is saying, it was very interesting even without the slides. So no worries about that.
Yeah, I got the chat set up now as well, so I try to monitor for any questions. Let's see if that works out. Yeah, and some news articles about confidential computing I just talked about, and these are the two services, Signal and the eRezept. Yeah, and where I left off was we now see all those confidential computing offerings popping up at the cloud providers. We have a very vastly growing ecosystem there of confidential computing technology that you can already use today to secure your workloads in the cloud. But this is just the very high overview. So I'd like to go a little bit more in detail to explain what this actually is and how we can achieve these isolated, secure environments in the cloud. So the most prominent example and one of the first concepts of confidential computing was from Intel, the SGX enclaves. So the general idea was that you're typically cloud stacked. You have this hardware and you have your operating system hypervisor, all this orchestrational layer, and finally you deploy your application. And without anything in place, you have to trust all those layers and all the people and the companies that have access to these different layers. So now with confidential computing, and especially with SGX enclaves, the idea was that you add something to the hardware, in this case, a instruction set extension that would allow you to create isolated processes on your top layer. And those would contain your data and your data and your code. Those would be measured when the process is created and would be verified that that you have integrity there, and then would be executed. And the processor and the hardware would make sure that no other layer here could access this code and data. So a couple of features that we see in enclaves in general, and that come with SGX is, first of all, you have isolation. So as I said, no other layer can access code or data that is executed inside such a secure enclave. And you also have runtime memory encryption. So at runtime, even if you would physically have access to the main memory of the process, you would not be able to steal any code and data. And to make this useful, one of the most important aspects is the remote attestation. So from inside this enclave, you could prove to the outside world that you are running inside such a protected environment. You can also do this from the outside. So you can also do attestation from that. You can also from the outside attest that something runs inside an enclave. And from there on, then you can build your applications and systems, and you can provide to your users, to your other components, that you are secure and data can be shared with you securely. And finally, they have a mean of sealing state. So you could start and stop your process and store data, for example, to disk, and later on unseal this data only if you are running the same enclave with the same identity again. So you don't have to worry that your persistent data and the state of the application might be leaked later on. This process-based enclaves, or these SGX enclaves, have some limitations. They have a limited system interface. So it says no syscalls, but you could essentially, it has a limited set of syscalls you can do that are specific to SGX. But in general, they don't have access to the system's syscall interface. Every time you do a syscall, you would leave the enclave, process the syscall in the operating system, and then jump back into the enclave. And this has, of course, a lot of downsides. You can't just lift and shift your code and data. You have to specifically repackage, rebuild your code to run in those process-based enclaves. And one development we see very recently is that to allow for real lift and shift and to not have to repackage, rebuild things, a new confidential computing technology called, typically named the confidential virtual machines, short CVMs, that not only run single processes inside secure enclaves, but running a whole virtual machine, including the operating system, inside such an isolated environment. So you have the same idea. The hardware provides, let's say, the hypervisor, which is not trusted, to create such a secure virtual machine, then load your image securely, measure it, and then you can execute whatever you want there. And this gives you the ability to essentially do real lift and shift, and you have the same type of features of isolation, runtime memory encryption, and remote attestation. So to compare those technologies, we have, let's say, we typically differentiate them on something we call the trusted computing base, which is all the components you have to trust inside your trusted environment. If you use SGX, for example, to just protect individual functions, so you split your application and only individual function calls enter a secure enclave, this is the smallest you can go and requires highly adjusted applications where you specifically develop towards this interface. The second thing then that somewhere in the middle is where you package whole applications inside process-based enclaves. And this means that all your code is running inside the enclave, so slightly larger trusted computing base, still some repackaging, probably recompilation and this kind of stuff needed. And then the confidential virtual machines on the right side, where you have to trust everything that runs inside this virtual machine, the whole operating system that also has a larger attack surface from below, of course, because now you assume the hypervisor or anything that runs there can attack your kernel from below, which is, of course, a lot of things that could go wrong there. And then you have all those components that run in there that you have to trust. And examples of these would be the AMD SEV, Intel TDX, or something that's going to be happening soon. It's called ARM Realms. And the idea here is that you have lift and shift functionality for existing workloads. Something that's somewhere in between those two worlds is the AWS Nitro enclaves, which are running entire virtual machines essentially, but their packaging mechanism and their feature set is also slightly related more to the confidential containers, if you will. So it's hard to really fit that into this picture here, but just to mention it, somewhere in between. And we build open source software to make these technologies accessible so you can build workloads, you can deploy stuff to the cloud that utilizes these hardware technologies to protect and isolate your deployments and your data. And we have similar concepts in our products. We have 3 tools that are intended for more these process-based solutions, especially Intel SGX. And we see the fit here if you want to create new types of solution, new type of applications that build on the concept of confidential computing, that maybe implement a use case that's only possible in such secure environments like multi-party computation, AI training on PIA data, so personal identifiable information data, and these kind of things. And then on the right side, we have a tool that we just released last week that is using confidential VMs to create entire Kubernetes clusters inside such execution environments. So you can think of running a Kubernetes cluster in the public cloud while being completely isolated and don't have to trust any part of the public cloud of the cloud provider that has no access to your cluster whatsoever. So if you want to lift and shift, this tool is intended for this use case. For this talk, I'm going to focus more on the left side on how you can develop cloud native applications, maybe repackage cloud native applications to run inside process-based enclaves, how you can orchestrate and scale them, and then finally integrate them together in Kubernetes to build scalable confidential applications. The first tool I'm just going to mention here briefly is called Ego. When we started, we noticed there is no Go runtime for confidential computing or for enclave SGX. So what we did, we basically slightly modified the Go compiler so it doesn't do syscalls, but instead goes into a compatibility library that handles the syscall layer so it can run inside secure enclaves. And then we try to make the simplest tooling possible for you to interact with and package and build your applications. So it feels like just any other Go development process without going into the troubles of understanding how to build and package into SGX enclaves, which is or can be quite troublesome. So we have 3 simple commands. You build as you would do the Go compiler that builds a Go binary, and then we sign it because every SGX enclave has to be signed. And this step also packages your whole enclave. And then you can just run similar to how you would do Go run, and it will load your enclave and run your Go code inside there. And yeah, this is, for us, it feels very natural to our usual Go development workflow. And we use this for bringing Go applications, and most cloud native stuff is written in Go. So we can bring most cloud native stuff to those secure enclaves. So we can already isolate and protect our individual workloads, which is cool. We have an example of where we, for example, take HashiCorp Vault, the key value store of HashiCorp that's often used to distribute secrets, for example, to run inside a secure enclave. And when we had that, we have protected our individual workloads. Of course, there exists other tooling for other languages. There exist some library assets that can more or less run a variety of different languages and different types of applications. So we had we built the Go part, and then we could lift and shift or most of the workloads in the cloud that we needed to into secure enclaves. And then the second problem arises, and the question then was, okay, now we have individual workloads. How can we bring them together for a modern cloud native architecture? How can we do a microservice system and connect those individual services securely so we can distribute and share data between those services while everything is end-to-end secure, end-to-end confidential? And how can we orchestrate that as we would usually do with Kubernetes, while everything inside Kubernetes, all the Kubernetes components, our nodes, our control plane, they are all not trusted because they either completely controlled by the cloud provider or running inside cloud provider controlled infrastructure. And therefore, we came up with a project called MarbleRun. So the idea is that we can use the existing orchestration tooling of Kubernetes, and we add a trusted party to that runs let's say a trusted control plane that takes care of all those orchestrational tasks that you have with distributed confidential applications. So a confidential deployment for us means, of course, individual protection of our workload. That means runtime encryption of data. And then we need to somehow be able to verify the topology and functionality of our application. We need to make sure that any part of the infrastructure of the existing orchestrational layer is not trusted and can't access our protected workloads. So the administrators, the cloud provider, and anyone that has access to the cloud infrastructure, either intentional or through some malicious act. So the concrete questions we solve with MarbleRun are how we can attest the integrity and confidentiality of one container or one pod, if you will, to another. So if one service wants to share data with another, how can it make sure that the other one is also running in a secure enclave? And then how can we verify this entire deployment that might scale up and down the whole time as one concise application from the outside? So clients, administrators can verify this before interacting with it. And then one very specifically technical thing was we wanted to provide some form of mutual TLS. So you can essentially have something like the TLS offloading that is often done by service mesh solutions. But we can't use the existing solutions because they don't terminate their TLS connections inside the actual application, inside the container. They terminate inside the sidecar and then go through localhost. And we can't trust localhost because it's cloud infrastructure. So we need to terminate our connections inside the application, inside the actual enclave. And then, yeah, some orchestrational tasks, like how can we distribute secrets? Kubernetes is not trusted, Kubernetes control plane and etcd and everything is not trusted. We can't use the usual way of configuration and secrets management there. And we also want to make this whole thing updatable, scalable, all this kind of stuff. So in MarbleRun, what it would look like from a workflow perspective, you would install your usual orchestrational little things, have a Kubernetes cluster, maybe install a service mesh like Linkerd, and then you would install MarbleRun. It would install the MarbleRun control plane, which we typically call the coordinator. So if you hear me saying coordinator, this is the control plane piece. It runs inside an SGX enclave, so it's protected itself, and it can be verified from the outside. So a DevOps engineer can verify it and provide it with a configuration. And this configuration we call a manifest that contains how our confidential application should look like. Similar to how you write your YAML files for Kubernetes, you would describe how your individual enclaves can be identified, what their measurements are, how they should be configured, what secrets they should be provided. You can define some role-based authentication things in there, some secrets, some mutual TLS configurations, this kind of stuff. So you define it there. And then you would install your application. And your application would be built with Ego, with one of the other enclave runtimes for your workload. And they would come up, boot up, and then they have a small, a small shim layer that connects to MarbleRun and is authenticated according to the manifest that you specified earlier, and is then provided with secrets, configurations, and TLS credentials. And these TLS credentials can then be used to connect those services together. So they are used in those mutual TLS connections to the other service, and they have a root of trust in a root certificate provided by our MarbleRun control plane that then can always be used to authenticate other services in your service mesh. So now we have a fully connected application, everything's running smoothly, and then a user can go ahead and connect to your front-end service, for example. And similarly, the user can connect to the MarbleRun coordinator, obtain an attestation statement that contains a hardware-based, for example, SGX attestation statement that can be verified, and then also contains this root of trust, this root certificate that is then used to verify every connection, or potentially verify every connection to the application. So you set this root certificate and then connect your front end and verify the TLS connection by doing so. So this is the general workflow of how MarbleRun takes care of orchestrating. So if you would now, for example, scale up, another container pops up, it connects to MarbleRun, it's authenticated, provided with the credentials to join this mesh together set of confidential services, and then just works as usual. And from the outside, we can always verify the entire deployment using the MarbleRun coordinator. So putting this all together with Ego and of course the other enclave runtimes with MarbleRun, and something I haven't mentioned at all today called Edgeless DB is essentially a database that runs entirely inside secure enclaves and has some enhancements to its storage encryption. So it's more or less a MariaDB front end coupled with a slightly modified RocksDB backend for a end-to-end secure database. So we use this if you need a storage solution that needs to be confidential computing graded. And then we package together this with MarbleRun, and we can build an entire end-to-end confidential cloud native apps. And in most cases, no code change is required if we're using Ego or library as runtimes. And one example of this is the Open Service Mesh bookstore demo. Open Service Mesh is a service mesh from I think it's a cloud. It's part of the CNCF now, so CNCF project, and they have a demo application called Bookstore, and we confidentialized it using those 3 components. If you want to take a look, we have a blog post on how we did that. So please check it out. I have a smaller demo that's not that complex and can be quickly shown prepared. Let me switch to the console. So I have a cluster in Azure prepared that is able to run SGX enclaves. We can verify this by running kubectl. First of all, we have 3 nodes. So let me describe one of those nodes. You would see a lot of things happening here, but you would see this node exposing free resources regarding to Inflow SGX. So this node is equipped with the latest SGX hardware and has the capabilities to run SGX enclaves in there. And there's not much running so far. There's some SGX device driver specific things, but so far it's a vanilla AKS, Azure AKS cluster. And I can install MarbleRun there, doing MarbleRun install. That goes very quickly and installs the control plane. And we can wait for this to finish running check. And the application we're going to install here is a very simple demo application from the Linkerd service mesh that provides a emoji voting platform that is 3 services, 1 front-end service with a web interface, and then something that counts the votes, so more or less a stateful service, and 1 service that provides some application logic. In this case, it provides emojis. So when MarbleRun is ready, we should be able to configure it.
In the meantime, there's a question for you in the Q&A box. I don't see.
Oh,
if
sorry,
you can...
the Q&A box.
No, it's okay. While we wait, maybe you can answer. There's a question. Can you see the Q&A box?
One sec.
No problem.
Add the chat open. No, I need to go back to.
I can read it from. I can read it to you if you want.
Oh yeah, please go ahead.
So Jan Bosniak is asking, can you share some performance benchmarks? I'd be curious where would be most overhead, if any, whether it's enclave startup or per syscall/ego ocall.
Well, that's a good question. There, especially with process-based enclaves, there's can be quite some overhead. The enclave startup is not too bad. I can't give you exact numbers on that, to be honest, but the bigger performance impact is definitely if you have a lot of ocalls. Ocalls means you do a syscall and your enclave has to exit the secure environment and then return back later on, handle the syscall in the operating system and return back. So for example, if you do a lot of IO is handled by the system. The enclave can't do this on its own, even though there are people implementing switchless sockets where you don't have to exit the enclave context. But nevertheless, if you have a lot of those, your performance impact is going to be bigger. And this, with the latest iteration of SGX, with the isolate machines, they were able to reduce this overhead by quite a lot. So you're usually able to go below, so go into single-digit percentage overhead, but it's harder to say this in a general manner. It's usually depending on your type of application. But I would say you can make it happen to definitely go into the single digits. And we had implemented in an AI pipeline even where we were able to comparing CPU inference and training compared also CPU only on Intel, comparing enclave to non-enclave, and this was almost negligible, the overhead. So you were close to no overhead in there. Obviously, it's less I/O than some other application maybe. Let me see what's going on here. All right, this maybe just took too long. So now I can expose the MarbleRun coordinator API to localhost. Just to simplify this, of course, you can also expose it externally, but for the sake of the demo, just copy this command. Let's just port forward this service to my localhost. I can quickly access it, and then I can obtain the MarbleRun root certificate. So this root of trust and the MarbleRun CLI I'm using here is automatically verifying the integrity of my control plane. You can also do this by hand or verify the given attestation statements by hand, but the CLI does this for me automatically. Okay, and let's save the certificate somewhere here. All right, and now I can use this certificate to authenticate all other connections to either to any of the services in my cluster. So this is all I need to do to set up MarbleRun. So I can now go ahead and configure my deployment, and I have a manifest laying around for the emoji voting application. Let's quickly take a look. It's in JSON format. It defines some packages. Think of it as the containers of your application. It contains the measurement of the enclaves that run inside those containers. And next to packages, let me scroll down a bit. I'm going to skip infrastructure. Is marbles. And it's called MarbleRun for a reason. So these marbles are more or less mapping to the pods inside your Kubernetes cluster. And each Marble essentially has a package. Think of it as like the container, the enclave, and then the parameters that this package should receive. And this could be anything like environment, files, anything like that. And in this case, we also define a TLS tag for some manual mutual TLS configuration here, but they would automatically be provided with an automatic mutual TLS tag if I wouldn't define it here. I have let's skip clients and roles. There are no roles or stuff defined. I could define roles like somebody who's able to update certain packages, somebody who is able to recover if this whole thing for some reason needs to be restarted or so. But let's skip all that. There's a secret defined, and the secret in this case is a certificate that should be signed by the MarbleRun root certificate. And this secret is then later on used in my TLS configuration a little bit down below, where I would say, okay, all incoming traffic from my web front end should use this certificate to show to the clients. And then I say, okay, my emoji, which is the application logic service here, should accept incoming traffic on using TLS on port 8080. Same for the voting service, and my web service connects to those two services. So it has outgoing connections configured in here. You will find this in our GitHub repository. We have the Emoji Voto app has a GitHub repository. So if you're interested, take a look to have a bit more time to understand everything that's listed in there. But I can deploy this manifest simply using the CLI. And then I can, at any time, at any point in time, I can verify that this exact manifest is deployed, is set for this deployment. So any party could do MarbleRun verify. There's an API for that, so you can of course use the command line interface, but any client can use just the API to do the same operation, verify that the manifest that is deployed remotely in my cluster is the one I have locally in here. And of course, I just set it, so it should be okay. And from that point on, I'm done configuring MarbleRun. I can install my actual application. I'm using Helm in this case, that installs the Emoji Voto app. And then I can wait for the whole thing to come up. Might take a bit. And then if this is done, I'll be able to access the web front end, and I'm gonna do a local host port forward again because I haven't set up a public IP address for this AKS cluster. All right, let's see. Are there more questions in the meantime? No. Last one is coming up, so let me prepare the port forwarding. So let's say I do 8080 on localhost. And then go to my web browser. Oh. Oh no, this is running inside my VM, so I need to expose it on right. And it will show me a certificate error because my browser doesn't know the MarbleRun root certificate. I could, of course, configure it so it's it will has this as a root certificate, and then my browser would know the could verify this this application certificate, and then I'm connected and I can use the application as usual. All right. So in conclusion, CC makes systems end-to-end secure and verifiable, creates those secure environments in the cloud, so you can use you can shift your workloads in there without the risk of leaking it to any malicious party or potential actor in the cloud. If you're interested in those tools I just showed you, go to our website or our GitHub. You find everything on all the links in there. You will find the tools. You will find the demo I've just shown you. If you're interested in the topic in general, we had as I said, a conference last week with people from the whole industry, with a keynote from the Azure CTO, and everything from this conference will pop up on our YouTube. I think you will find the link either on our website or you go to YouTube and search for OC3. And yeah, I also gave a talk similar to this one, where I also introduced the Constellation product we released last week that that allows you for this true lift and shift if you don't want to build new applications or have the small TCP as I've just shown you right now, but just want to lift and shift everything into a private environment cloud or in a private Kubernetes. Definitely check out this one. And yeah, that's it. Thank you very much.
Excellent. Thank you so much, Moritz. It's been really, really interesting. We are going to go directly to the next talk right now. Please remain online if you would like to ask more questions. We're going to have a session right after the last talk. So basically, if you would like, you can also post them on the Q&A box and I will redirect them directly to Moritz in the meantime. But without transition, we jump directly to Melissa. Thanks a lot, Moritz. And Melissa, the stage is yours.
Great. Glad to be here, everybody. I'm so glad to, I know we've been in this pandemic now for the last 2 years, but one of the advantages is being able to go to Switzerland without actually going to Switzerland. But one of these days I would love to visit Switzerland. But I am currently in Denver, Colorado, and enjoying the opportunities for virtual events here for now. Let me go ahead and share my screen. Okay, so today I'm going to be talking to you a little bit about Distroless images and securing your Docker images. I'm not getting into super detailed information. This is pretty high level. I think it's very easy to use containers, and especially with this particular audience, this is something you do every day, but it's easy to get caught up in just using them without thinking about what's going on under the covers. So in the build up to talking about Distroless containers, I want to just talk about containers in general and what's going on under the covers. This is kind of a modification of a talk that I've done in the past. There is a lot of discussion of Docker in this talk, but just understand this isn't a deep dive or a tutorial on Docker or anything. There's lots of good documentation already on that. So I just wanted to do something a little bit different and maybe go back and look at the history of containers a little bit and how we got here. All right, a little bit about where I come from. I am Melissa McKay. I am currently a developer advocate with JFrog, but for over 20 years prior, I have been a software developer and engineer in various roles in various companies. Primarily, my language is Java. I worked on Java server-side services, but I rarely meet a Java developer these days that aren't involved in other types of services and languages, especially when we started, going toward microservices and getting smaller services out there up and running. So I definitely have experience in others as well. My most recent experience in software development prior to becoming a developer advocate kind of pushed me into some new territory. This was while I was working on some teams practicing DevOps. And I did get the privilege to learn more about how the apps I was working on were actually deployed. And I got an exposure to a variety of tools in the DevOps ecosystem. And one of those tools was Docker, of course. And that's actually how this talk came about originally. I just started collecting information from my own experience, learning, getting ramped up, and on how to containerize my apps. And some of that was trial and error. So I have some funny stories about that. Here's my contact information. You can always, find me on Twitter, of course. I'll go ahead. These slides will be made available, but I'll go ahead and put my Twitter handle in the chat so you have it. And I recently became a Docker champion or a Docker captain and a Java champion at JFrog a couple of years ago. So that was pretty exciting. Okay, JFrog loves to give away stuff, so I can't skip this. You can go to this link. I will go ahead and put that in the chat as well. And JFrog will give you a chance to enter and win a pair of AirPod Pros. So you can enter with the QR code or the bit.ly link, of course. And actually I guess that's a bit.ly link. And then a winner will be selected within 3 business days, and they will contact the winner via email. And once the winner accepts the prize, they'll share the winner's name in the meetup group with the community. So don't miss that. Exciting. Okay, today's agenda, I'll go through container history. I'll go through a little bit about containers in real life. We'll review some of the container gotchas. A lot of you, this might be review, but sometimes we need to be reminded of these things. And then I'll get into Distroless images and what those are about. Okay, so let's jump in and start learning about containers. I know that's not the graphic you were expecting, but I made a commitment to myself not to use any shipping container pictures in any talks about containers ever again. I think I've seen those too many times. So this theme is bananas. I hope you enjoy it. And I just want to talk more about how our industry has adapted to dealing with resources over time. And when I put these slides together, I was reminded of a story that my grandfather would tell me when I was growing up. He grew up in some pretty hard times in Depression era in the US. And when he was a kid, they would be gifted a banana at Christmas. And this was probably in the 20s or 30s, so quite a while ago. But bananas were such a rare treat. And my grandmother's family or my grandfather's family, they would get this banana, they would scrape the peel with a fork to get every last bit they could off. And that might not be the most solid analogy, but I think of that story when I think about how computing resources were in the 1960s and 70s, very limited, very expensive. It took a lot to get anything done, and often a computer would be dedicated for long periods of time for a single task for a single user. So these limits on time and resources created bottlenecks and inefficiencies, and just being able to share with each other wasn't quite enough. We needed a method to share without getting in each other's way or having a person inadvertently cause an entire system to crash for everyone. So this required a need for better strategies in sharing compute resources. And that actually started a massive path of innovation that we see a lot of benefits from today. And there are some key points in time that I'm going to bring up. There's a lot of other things that happen, of course, but these are some highlights that brought us to the state we are today with containers. And I'm just going to start with to root, change root. This was born in 1979 during the development of the 7th edition of Unix, and it was added to the Berkeley software distribution in 1982. This ability to change the apparent root directory for a process and its children resulted in a bit of isolation in order to provide an environment for testing a different distribution, for example. And that was the thought when this tool initially was entered into the source code, that it would be used for testing purposes. That Chroot was a great idea, solved some specific problems, but more was needed, of course. And the jail command was introduced by FreeBSD in 2000, which is more sophisticated than Chroot, and it has additional features to help further isolate file systems, users, and networks. And it had the ability to assign an IP address to each jail. Moving on in 2004, we came across Solaris zones. Those brought us ahead even further by giving an application full user, process, and file system space and access to system hardware. And Solaris zones also not introduced, but highlighted the idea of being able to snapshot a file system, which becomes pretty important when you're running containers. And then in 2006, Google jumped in with their process containers, which are later renamed C groups or control groups. Those were centered around isolating and limiting the resource usage of a process. Moving right along in 2008, C groups were merged into the Linux kernel, and that, along with Linux namespaces, led to IBM's development of Linux containers. Then we get to 2013. This is a big year. Docker came on the scene with bringing their ability to package containers and move them from one environment to another. That same year, Google open sourced their Let Me Container That For You project, which provided applications the ability to create and manage their own subcontainers. And from here, we saw the use of containers and Docker particularly explode. In 2014, Docker chose to swap out their use of that LXC toolset for launching containers with libcontainer in order to utilize a native Golang solution. When I first realized Docker was written in Go, I was surprised. I really didn't have any idea. So that was an interesting bit of trivia. Skipping over some details, there's a lot of different projects that were started, organizations and specs that came out, but there was one event that is really important in June 2015. This is important to know about because it gives you some insight into some of the activity and motivations behind shifts in the market as with regard to containers. The Open Container Initiative was established. And this is an organization under the Linux Foundation that includes members from many stakeholders, including Docker, with the goal of creating open standards for container runtimes and image specification. And while all of this is happening in the container world, there's a couple of other dates that are going to be important, especially to Java devs. I'm being selfish and I'm going to tell you some Java stuff a little bit here. A bit of trivia for some of you. Java 7 was released in July of 2011, and work was started on Java 8, which was released in March of 2014. So when you start containerizing Java applications specifically, this a little bit of history is important to know because there's some issues there with this development of Docker alongside development of Java. There were some misses and disconnects there that were fixed much later. All right, what exactly is a container? Let's just take a quick look at a real life container itself, what it actually looks like on your system. This is something I did first thing when I started learning about containers in general. I'll just show you how it's stored, what's actually happening under the covers. This is probably more important for those who deploy maybe containers, by themselves, not necessarily using orchestration, but still good to know. There's some things that can happen if you aren't paying attention to how the file system is being used. My first experience, I was a developer on a new project with a tight deadline. Of course, that's usually how it is. I could argue that's how most projects begin. And the best course of action for me was just to jump in and start getting something up and running on my machine. I'm very hands-on. I want to do it and see what happens. And the Docker documentation actually is really good. I have a link here on this slide to that. easy to find, of course. So if you find yourself in a similar position, which I'm sure that's in the past for most of you, but I definitely recommend going to their Getting Started docs, which I've listed here. And the first thing to note is just that a Docker image is really just a tarball of a complete file system. And when an image is unpacked, it's thrown into its own directory, which becomes its root file system. The second is that processes that are involved in running those containers are just regular Linux processes. On top of that, there's just a few Linux features that are used together in a way to achieve that isolation that we expect from containers. Namespaces are important. This is what is used to provide virtual separation between these containers. This is how the processes inside one container don't interfere with the host or with processes inside another container. And here you can see the namespaces that were set up for a Postgres container that I have on my machine running. Not today, I turned it off today to clean it up for you guys, but I just pulled some screenshots of, and I'm on a Mac, by the way, so you'll see some Mac commands as well. The C groups functionality, also essential in constraining how much a container can use things like CPU, memory, network bandwidth, etc. And I can set these constraints by including options on the Docker run command when launching an image. And of course, these can be set using orchestration as well. You're not necessarily stuck with the Docker runtime either, but this is for development on a local box. Here you can see I launched a container and I constrained the memory limit of my containers running. And then just some more details on the file system where containers and images are actually stored. First off, after you've installed Docker, running the command Docker info will spit out a ton of information about your installation using the Docker root directory. And this is where everything you're going to care about regarding your Docker images and containers will be stored. If you're on a Mac, of course, these are actually running in a tiny VM. So you're going to need to use some utility. I used to use Screen, but it's not real consistent and available. So it's not working for like later versions. So in order to get into this directory to just kind of look around and see what's going on, I have a command here, a Docker run command to start another container that actually enters the UTS namespace, the network namespace, and the IPC namespace, and it targets that PID of 1 so that you can get some information about this root directory. It's pretty interesting just to navigate around in there and see how it changes when you launch containers and remove images and things like that. Later version of Windows, I actually have a Windows box on order. It's been years since I've been on Windows. I swore I'd never go back, but the latest WSL stuff that they have on I don't think it's Windows 10 and up, they have the capability of running Linux containers natively using WSL, the Windows subsystem for Linux. That there's a path here where I did find where the root directory can be found on a Windows system. So I'm excited to get that machine up and running. It'll be a while before it gets delivered here, but it'll be cool. All right, this slide shows just some information about where the images are stored on your system. I have my available images. I just use the Docker images command to see them. I have several installed. I just showed a couple here. I can inspect any image by using its image ID, and this spits out a ton of information. But what I want to highlight here is the graph driver section, which that contains a bunch of paths to directories where all of the layers of these images live. So Docker images are composed of layers. Most of you know this already. Those represent they correlate to instructions in the original Docker file that was used to build the images originally. And these translate into directories, and these layers can be shared across the images in order to save space. The lower dir, merge dir, and upper dir sections are important. The lower dir directory contains all of the directories or layers that were used to build the original image. These are read-only. The upper dir directory contains all of the content that has been modified while this container is running. And if modifications are needed for a read-only layer in lower dir, then that layer is copied into the upper dir where it can be written to. This is called a copy on write operation. And it's really important to remember always the data in the upper dir is ephemeral data. It only lives as long as the container lives. So if you have data that you want to keep intact, obviously you need to use mounting or volume features and to mount a separate location or a separate drive or to access a database, that kind of thing. Lastly, the merge dir is kind of like a virtual directory. It combines everything from lower dir and upper dir. And this way, this is how the union file system works. Any edited layers that were copied into upper dir will overlay the layers in the lower dir. So if you were to exec inside that container, that's what you would see. This is just an example of a few containers that are running on a system. I've got a JFrog container registry installation. That's pretty old, by the way. I don't think we have that available anymore, but it includes a container for Artifactory and a container for a Postgres database. And the other is just a simple test container I was playing around with. The container IDs of the running containers match up with the container subdirectory names. That's something to remember. If you stop a container, that corresponding directory doesn't automatically go away until that container is actually removed with the docker rm command. So if you have stopped containers lying around, especially on your local system that never get cleaned up, or even in your test systems, you might see available space start to dwindle. So take care that you're cleaning up after yourself. There is a Docker system prune command. I use that regularly when I do Docker workshops, just because I want to start fresh. You can run that to help clean things up, remove all images, remove containers, that kind of stuff. Or you can launch a flag to indicate that a container should be removed when it's finished running. Obviously, this stuff is also taken care of in orchestration frameworks as well. Let's make sure to use them. So these tool sets around building and running all of these images have made things so easy. It's also easy to shoot yourself in the foot in a few places. It can be deceptively simple for especially people just learning and starting. So I'm just going to go over some of the most common gotchas pretty quickly. I'll include some JVM specific gotchas as well that I ran into immediately when I first started working with containers. The first, of course, is running as root. I'll be honest, when I initially started, I was so excited. I just didn't really take this one seriously enough. But now that, that processes inside a running container are just like any other process on the system, it's scary now to run as root inside a container. And doing that opens up the possibility of a process escaping the intended confines of the container and gaining access to host resources. Reducing that attack surface of your container by following the principle of least privilege, that's important. And although containers are designed not to affect other running containers, they will. If someone gains access to your container and immediately has root privileges, they can wreak havoc on your host as well. So how do we mitigate this problem? The best thing to do is when you're building images, initially make sure that you are creating a new user. You can use that user command inside the Docker file when the container is built in order to run processes as that user. And you can also specify user just when running the Docker run command, but that leaves open the possibility of forgetting to do that. So it's nice if it's just built in and your production image is set up by default not to run as root. Many companies by now have set up policies and stuff to prevent this from happening. So, but I have been on teams where this was not paid enough attention to. Also pay attention to these official images that you get from Docker Hub. You need to know whether or not they run as root, or if you need to, build another image on top of those to fix that. Even though Docker provides you with the ability to set resource limits on your container, it doesn't automatically do it for you. The default settings are free for all with no limits. So make sure you understand the resource needs of your application. Too little and your container will die from starvation. Of course, too much, and the container could smother others on the system. The resource usage of your containers, that's something that you want to monitor over time and adjust as needed. And it's good to determine if something is going wrong or if load on your system has changed for some reason. You can use the monitoring information to determine if your application needs to be split up further with certain actions scaled differently. I went into a whole process with that on a team of mine where we divided up our application into smaller pieces and were able to scale like our front end very differently than the back end services. And then never updating, of course. This is a huge security issue, and it's easy to get complacent, not pay attention to what's actually being pulled when you build images. Not only do you need to be aware of outdated versions that you specify in your Docker file, but you need to pay attention to what's in the base image that it's coming from. Not updating these packages and libraries can, lead to some pretty embarrassing results, especially when there are tools available now all over the place now to alert you when security issues have been discovered with specific artifacts. And I'll show you an example of that in a bit. Even if you've gone so far, you've ensured your containers are running with a non-privileged user, there's still risk if there's known vulnerabilities that exist within your container or even on the kernel of the host. So from time to time, exploits are found. Those enable attackers to escape a container. So keep up with those security updates. This is a very Java specific one. This has to do with that in tandem development of Java and Docker containers. Pretty specific to Java applications, but still important. You never know when you need to containerize one of those. The JVM is pretty clever at automatically determining settings for your swap and heap and your garbage collection behavior based on things like the memory and the number of cores available on the host. And remember earlier in our lesson when I mentioned the dates for Java 7 and Java 8, considering the timeline of Docker and Java releases, Java 7 and versions of 8, and certainly earlier, are not fully container aware, meaning that your Java application won't necessarily obey those memory and CPU constraints that you put on your container. And you could end up with some surprise out of memory killer activity, which is exactly what happened to me. This means your Java application is not going to behave like you expect. The reason for this is the mechanisms that the JVM used in these older versions to retrieve the resources. Those actually were coming from the host machine and not the control group limits where you would expect them to come from. There were some improvements around container awareness that were introduced in Java 8 update 131. And there's further improvements in later versions, but to really get all of the benefits of container awareness, you really should at least get to Java 11. That's an LTS release. Latest, of course, that's come out is 17. So if you keep up with those, that'd be great. And then image bloat. This is a big one. I learned quickly about the Docker ignore file. So when you're building a Docker image, oftentimes you may hit a dot at the end of this command, the build command, which indicates, yeah, this is where my Docker file is. This is the context, meaning this is where I am in the file system structure that I want to send to the Docker daemon to build this image. Well, in doing that, you may be sending over stuff, and if you use one of these global copy commands in a Docker file, you could be copying things in like your .git directory, which probably isn't something that you want to have in a production image. I often see like copying an entire source tree in one line, which means one layer. That means if anything changes in that particular set of files, that layer has to be regenerated every time you build. So, organizing your code so that stuff that changes the most often is in its own layer. Maybe consider implementations in one layer and abstractions in a different layer. That's one idea. And then, of course, avoid, scooting in your secrets. If even if you go through the effort of like in your Docker file trying to delete stuff, they still exist in the previous layer because every layer is just a diff of the layer before. So not good enough to just go through your Docker file and delete things. I've actually seen that. It doesn't work that way. Also, learning how to use a multi-stage Docker build is a good idea. That's something relatively new to the ecosystem. Being able to build in such a way where you're not including extra packaging tools and things like that, like Maven, for example, or NPM or whatever. So you just have what you absolutely need in the final image that you've built. All right, Distroless. So all that build up to understand why people are looking at Distroless images. So, pulling in a large parent or base image, even if it's, relatively safe, official image from Docker, these could include a bunch of stuff that you don't need. It increases your attack surface area from a security perspective, and shipping these large images around and storing them can become clumsy and slow and expensive since we're all paying for storage these days. And this reminds me of, and I'm going to date myself a little bit, but remember when I had to pay, for every text I sent on my cell phone. I'm hoping at some point we'll get beyond this, paying for every byte that we're using for storage, but this is where we are today, so we need to manage our resources carefully. Also, Distroless containers actually, not only do they make a point to strip everything out that you don't need, you want just the minimum packages required to run your application. And this means even stripping the OS down to its bare minimum. This means no shell generally. So there's no execing inside that container once it's running out there. That's actually a pretty good security measure and something to consider. I know it makes troubleshooting a little more difficult, but if you're having to exec in a container on production, you've got some bigger problems going on. You can always, in your development process, you could develop, debugging type container or images in order to get beyond some of that. This is an example of a multi-stage build. So you can get a collection of Distroless containers from this link here. These are ones that Google built. They're built from Bazel. So, I mean, they're not using Docker to build these. They're just images that they've built and that they consider tried and true. Most of them, they're all based on Debian. I'm going to go ahead and put that link here so you don't have to type it in if you want to just go check out and see what they have. They just have a few and they're language specific. So we'll look at one for Java in a second. Anyway, this multi-stage build, notice that there's two from statements. The top one, pulls in a full-on OpenJDK image, and then the build happens. And then the line 7, the second from statement, that's the Distroless image. So the result from the first group is pulled into the second group, and that makes it very small image to end up with. Again, there's no shell, you cannot exec into this image. All right, and just one mention on managing your images. I'm going to bring up JFrog Artifactory just to show you what that looks like. Not going to give you a long spiel about it, but I did go ahead and pull up some images just to see what they look like, just command line. So we can actually see if these Distroless images are smaller. I love to just believe these statements, but I always want to verify. So let's just look at a couple really fast and see what they look like. The last thing I want to say about this slide is just I do have a dzone ref card on this for container registries, considering where to store your images and what to look for when you're looking for a container registry. Just note that whenever you're working with Docker on your machine, the default is Docker Hub. You're constantly going to be going out to the public Docker Hub. So that's something that they have recently set limitations on. So it's good to always have, a cached collection of images that you use in your system that you rely on. Okay, I'll bring this slide back up at the very end in case there's any questions that need to be answered, but don't forget to go to this link and get your earpods. But first, I just want to show you some images that I have pulled in. I pulled down an OpenJDK image from Docker Hub, and then I pulled down a Java 17 Distroless image from the Google store. And you can see these top two are the same. They're both OpenJDK. I just have one that's tagged with my JFrog instance so that I was able to push it up there to look at some more details about it. But these are actually both the same image. But look at the size of these. We're looking at 471 megabytes. Whereas the Distroless images, again, these are also identical to each other. They just have different tags because they're coming from different registries. That's about half the size, right? 231 megabytes. So that's pretty good, I think. When you start doing the math and have a lot of these out there needing to be stored or run or moved around in your infrastructure, that's a pretty big difference. Note the created date. So I just recently grabbed the latest OpenJDK here. This date, this is epoch. The reason it's like that is because these Distroless images are meant to be exactly reproducible builds. So, and the spec requires a created date. So, and putting nothing in there, you end up with epoch. So that's what that's about. These weren't actually created 52 years ago, but just something interesting to note. All right, so the next thing I do, I pulled these images down, I tag them, and then I push them up to my own container registry. And I'm gonna log in there and we're just gonna take a look at it. This is a free version of JFrog platform. And I pull these up every now and then when I do workshops and stuff, and other people can sign up for these instances. They're limited feature type things, but they're really good. These are all of the images that I pushed up here, and let's just compare. Well, there's two of them that we want to look at, this Distroless one and this OpenJDK one. So just to check something out here, it's said that Distroless images, because they have, less stuff in them, less content, that they should be more secure, less problems with the packages inside them. And these have been scanned by X-ray. And let's just take a look at what a Distroless looks like compared to the full-on OpenJDK image. So I'm going to navigate here to X-ray information. I'm not going to say anything about like what kind of security problems these are. I'm just looking at raw numbers at the moment, just for our benefit. This is something for you to do for homework if you want to, dig into these a little bit more and see what actual problems there are here. But this is the Distroless images, and it looks like we have 3 critical violations. We have, 31 security problems. Some of these are low that we may not care about. All right, let's go back to the full-on OpenJDK. Drill down into that image. Check out the scanning there. Here we have 3 violations still, but 94 security issues. There's still 3. There's a lot more medium issues. So it's just interesting. Whenever you're doing this, never take for granted that what is being said is true. In the past, when I have pushed up a Distroless image with like an older version of Java and stuff, in fact, the last time I gave this talk, this was absolutely reversed. And the Distroless actually had more problems, which was an interesting find. So today it's looking much better. All right, that's all I have for you. I know a lot of that might have been review for a lot of you, but I hope that it was fun and engaging, and you got some reminders of some things and maybe learned something new. Anyone have any questions?
Thanks a lot. Melissa, maybe some questions from the audience. We still have a few minutes for this session. I actually have one that I was thinking about. Maybe you've heard about Quarkus?
Yes. Yep.
Absolutely, right. It's for those who don't know, it's a runtime and framework to create Java applications specifically targeted for containers, and with very impressive results, right? Because I've seen like images like not even 10 megabyte big, and you're like, how can you even fit an application inside of that? So what was your experience with it?
Well, yeah, I mean, it makes sense, right? Because Java applications, you often get libraries pulled in with things that you aren't actually using, you don't actually need. And the problem with that is you go to these scanning things, the security scanning thing, and you find all of these problems, but they're things that you don't really care about because you aren't actually using them in your application. So Quarkus does very well with that, eliminating a lot of that and making your attack area smaller. Not pulling in libraries unless you're actually using them. So that would be a good homework assignment, is to get one of these, pull up some images, push up some images that are based on Quarkus, and see if, see how much of a difference it makes.
Absolutely. For what I've seen, the little I've been playing with it, you can create a classic jar or a WAR file, and you can put it inside of Tomcat and it would run anyway. So it really opens up the door to native compilation and also classic Java interoperability, which I think is a very interesting proposition in any case. So I was thinking about that, but yes, we at Vision
exciting stuff.
We try to make our container images as small as possible all the time.
So many improvements have been made with Java, because in the beginning it wasn't that good trying to containerize Java applications. Scared a lot of people away, but it's so much better now.
Exactly. The same problem happens with .NET. Many of these runtimes, or even the Erlang Beam machine, basically, when you have these big runtimes with managed memory and so on, they were created at the time where containers were not on the roadmap. So clearly they had to adapt. In that case, Quarkus has done its homework very well. So I don't see any questions from the audience, but maybe there will be more at the end. So Melissa, I invite you to stay until the end of the event. Maybe there's somebody comes up with a question by then. And thank you so much. It's been a great reminder of how we should be building our containers. Really cool and nice tips here and there. So that was really nice. Thank you so much. And now we go directly to Thomas for the last presentation of the day. That's about Cilium and eBPF. Thomas, the screen is yours.
Thanks a lot, Adrian. And hello, everybody. First of all, apologies for my voice. I've been sick the last couple of days. So if you hear a slight cough, that's from that. But in general, I feel fine. Let's jump in. Let me know once you can see slides coming up here. Is the screen visible already?
Yes, perfect.
Excellent. All right, so I will be talking about Cilium and eBPF. And my name is Thomas. I'm one of the creators of the Cilium project. I'm also a co-founder and CTO of Isovalent, the company that was created or founded by the creators of Cilium. Cilium is cloud-native networking security and observability. And before we go into more details on that, I want to just briefly talk about like where I am, where we are as a team, and so on. So Cilium has been created by Isovalent. We're a venture capitalist-backed startup with dual headquarters in Switzerland and the US. Switzerland because I'm Swiss and I love skiing so much, so I never actually moved outside of Switzerland, even though I've been working for American companies since forever I can think since I was 20. So I've been working for Red Hat for a very long time as a Linux kernel developer. And hence our team is basically split between the US and Switzerland. Our company is heavily focused on open source. Most of us have a background in Linux kernel development or open source in some other way. And we are heavily investing into open source. We're most well known for Cilium and also for co-creation and co-maintenance of eBPF. And obviously we'll dive into that some more here. But to make it very clear what is what and what we're going to talk about today, Cilium and eBPF Those are open source projects. That's the focus of today. Isovalent is the company behind it. If you are planning or if you are interested to run Cilium in an enterprise context, in a production environment, and you are desiring enterprise support, feel free to ping me and we can talk about that as well. That's enough of the sales pitch. Let's jump into the open source technology. So what is Cilium? Cilium is networking and load balancing foremost. Most of you probably heard of Cilium in the context of CNI, container networking interface. That's what Kubernetes requires in order for pods, containers to be able to communicate with each other across the network, because Kubernetes itself does not really have a networking model or networking implementation itself. But then Cilium can do so much more beyond that. Kubernetes services, multi-cluster routing, we can integrate existing workloads running on VMs or metal machines. We can do a whole lot of network security from segmentation, some of the service mesh use cases we heard earlier, including mutual authentication, but also identity-based enforcement and transparent encryption. And then even more important is the observability piece, where we can actually tell you what's going on in the form of metrics, flow logs, UIs, and so on. We'll dive into that. What is very unique about Cilium and why so many are so excited about Cilium and why Cilium is currently taking the world by storm is because of its use of eBPF. And if you've never heard of BPF or eBPF before, good news, we'll cover that in a brief moment. eBPF is at the core of Cilium and is why Cilium exists. In fact, our team has first invested about 1.5 to 2 years into advancing eBPF further to then build Cilium. So the whole reason Cilium exists is because of eBPF, by applying eBPF to the world of containers and Kubernetes. So what is this eBPF technology? It has a cute little logo like many other technologies, but what is it? Actually not very complicated, and you will get it in a nutshell because it's very, very similar to what JavaScript has done to the web browser, eBPF does to the Linux kernel or to the operating system. And you will understand this very, very quickly. eBPF is nothing more than the ability to run a program on a certain event. For example, when a system call is being made, in this case, a process is making an execve system call, we can then run a program to intercept that system call, perform some action, run some code, and return a verdict. For example, block the system call, or export some visibility, or take some other action. We can do this for a whole lot of events: system calls, network packets, IO operations, trace points, function calls, user space function calls. So you can even run an eBPF program when your own application performs a certain or invokes or calls a certain function. So very, very, very similar to how you can run JavaScript code when, for example, the visitor of your website clicks on a button or mouses over somewhere, you can run JavaScript code. eBPF does the same for the Linux kernel. It's as simple as this. Let's now dive into what this can actually do, because why is that important? That sounds neat, but it's not necessarily a completely new concept. Programmability has been around as a concept forever. What does it actually do? What does it enable? Here's a use case or a very concrete benchmark of one application of eBPF. There are many, many hundreds and thousands of different applications of eBPF. This is one of them, which I think is easy to understand and very impressive. This is a benchmark of HTTP visibility, and it measures the baseline, so no visibility. This is an HTTP benchmark, that's the blue bar. And then the proxy-based visibility, so this is using a proxy, such as whether it's Envoy, HA proxy, Nginx. Doesn't actually matter that much. They're all mostly the same. That's the yellow one. Extracting HTTP visibility. So visibility in the form of this request has been made, this was the latency of the response, and so on. And then in red, what is the latency difference to an eBPF-based in-kernel implementation of this, which does not require, for example, connection termination, and so on. And I know that this table will draw a lot of questions, or we'll pop a lot of questions. But this is an implementation that has been done where we can passively provide HTTP visibility with eBPF, and you can see that the latency is almost the same as baseline, whereas a proxy-based implementation actually adds quite a bit of latency. That's one concrete, very one concrete use case here. But if we take a step back and actually apply and talk about this a bit more broadly, eBPF is actually a lot more impactful. As I mentioned, my background has been Linux kernel development for about 15 years. And I often found myself in exactly this situation that somebody would come up and say, hey, I need to observe my app better, or I need this feature or this other feature, or I can remember when I was early on working on OpenShift, like the original versions of OpenShift pre-Kubernetes, OpenShift developers would come to me or come to our team and say, hey, we need this feature. Great, then we would work with the upstream kernel community to get this feature in, which by its own will probably take about a year or so, because it's complicated to do kernel changes and it's hard to convince all the other kernel engineers. But then it didn't actually end there. It would take years and years and years for that new kernel version to make it into the hands of users, because most of the users, in particular Red Hat users, would obviously consume Red Hat Enterprise Linux or another enterprise distribution. So it would take up to 5 years for the beginning or the ask for a change to the delivery of a kernel version that would actually function for that user. And by that time, the requirements of the user had likely already changed. So this made the kernel a very difficult place to innovate. Essentially, this meant that a lot of innovation actually moved to user space, while we have seen massive rise of user space networking, user space IO, user space security, things like gvisor, building entire abstraction platform for system calls, and so on, because the Linux kernel itself became very challenging to innovate in. We even saw entire forks of the Linux kernel, for example, for Android, because it was not possible to innovate quickly enough. eBPF is now changing this all of a sudden, because similar to how JavaScript has unlocked or has decoupled the browser version from innovation, right? Like if some of you have been using the internet for a long time, you probably remember way back when you had to upgrade your web browser to visit certain websites. When was the last time that you had to do that? Probably not recently, because JavaScript and auto programmability frameworks don't require you to do that anymore. And eBPF now unlocks the same for the operating system, in particular for Linux. So what used to take years can now be done within days, because we can dynamically load a program and change the behavior of the Linux kernel. Now that sounds potentially very scary to some of you, and some of you may even say, well, what is different to, for example, Linux kernel module? It was already possible to extend or to load additional kernel module code at runtime. This is where the difference comes into play. So eBPF, this is the entire eBPF landscape from a high level to a low level. And this low level here, this is the kernel, this is the operating system level. This is where the actual eBPF program will run. And part of this, you see a box called verifier and JIT, just-in-time compiler. This layer actually adds a sandbox concept, very similar to how containers are sandboxed as well. And a JIT compiler, which will take generic bytecode, generic eBPF bytecode, and just-in-time compile that into your CPU instruction sets. Very similar to how this is done for other interpreted languages like JavaScript or Java as well. This means that, yes, we can dynamically load a program very similar to a Linux kernel module, but we're actually running in a sandboxed program or sandboxed environment, very similar to how a JavaScript program is also sandboxed. The just-in-time compiler actually ensures that we can run as efficiently as if we recompile and restart our kernel or our entire machine. And then we have a kernel API, which actually ensures that our programs are stable and portable, which solves probably the lesser known problem of Linux kernel modules, which is that Linux kernel modules are very, very hard to make portable across arbitrary kernel versions. So these are the problems that are solved by eBPF, and all of a sudden, the kernel space becomes a place of innovation again, which is amazing because the kernel is a truly powerful place to run code in, because the kernel can see everything, the kernel can control everything, and we will see examples on how that can be used. So that's the lower levels of eBPF. And if you look very clearly or very, very closely, you can actually see a Windows logo there. Even though eBPF is coming from Linux, Microsoft has recently ported eBPF over to Windows as well. So eBPF is now available on Windows kernels too. On top of that, you see a bunch of SDKs and libraries, which will make eBPF programmable in higher level languages, because most of you will never want to write an eBPF program in assembly bytecode. So you can use Python, Go, C++, C, Rust, or other languages to actually write eBPF programs in. And then you can take it to an even higher level, which is the eBPF projects or the end user facing projects, such as VCC, Cilium, Falco, Catron, eBPF Trace, and so on. An ever-growing list of eBPF-based projects would actually solve use cases for end users. In the next step, we'll now focus a bit on Cilium, but I wanted to give a high-level intro into eBPF first, because Cilium is obviously not the only eBPF application out there. In terms of governance, eBPF has been, or we, together with some of the other industry members that have been involved in eBPF for a long time, we have together created eBPF Foundation. It's a Linux Foundation-based foundation. You can see the founding members here. Since then, the members, or the list of members, have been extended quite a bit, and the eBPF ecosystem is growing very quickly. But let's now shift gears into Cilium and actually look at what type of application, what type of services, what type of values can we provide with eBPF. So if you go back in here, you can see on the picture here, Cilium is kind of in the middle of a world that shows Kubernetes, Mesos, Docker, Istio. Today, it's mostly Kubernetes, of course, but in the end, Cilium and eBPF is actually very generic and very applicable to everything. As we will learn, it's not even limited to containerized applications only. Cilium adoption here, you can see across the board, this is not even inclusive at all, but from big SaaS providers to cloud providers, for example, GKE, EKS Anywhere are already using Cilium by default. Alibaba in the high performance option, DigitalOcean, various other smaller Kubernetes distributions are using Cilium as the default CNI to provide networking and security. And then from telcos to financials, Cilium and eBPF is very applicable to a very wide stream of use cases, and thus adoption is wide as well. As we now start to dive a little bit deeper here, I'm going to offer kind of this stage or the journey of what users typically go through when they apply or use Cilium in a Kubernetes environment. And if you want me to dive deeper on any of them in particular, feel free to mention that in the Q&A window. I have that open in another screen so I can actually see that and can dive deeper on that particular topic. So first of all, in stage one is typically what we're seeing when you get your initial Kubernetes cluster up and running. This is where you need basic pod and service connectivity, and you will also probably care about initial cluster hardening. So for example, making sure that Kubernetes RBAC is configured correctly, making sure that you haven't accidentally exposed your Kubernetes dashboard to the world, and so on. You might also be deploying something like container image scanning. In this stage, of course, you can pretty much use any CNI because all you need here is basic pod and service connectivity. You don't have additional security or scalability requirements. As you go into stage two, which we usually say you enter when you run sensitive data workloads or you have multi-tenancy requirements, so you have multiple teams running on a single Kubernetes cluster. This is when you start caring about zero trust network security, transparent encryption. You might want compliance monitoring, what is encrypted, what network policy violations are happening, and so on. Also, you want to monitor your applications. For example, measure the HTTP latency of your services, or identify how many HTTP 500 error codes are being returned, and so on, to build, for example, the typical golden signal dashboards. Also, you might have requirements around efficient load balancing already as you scale out, and you very likely need to integrate with external workloads which are not containerizable or which are not part of Kubernetes, and very likely they're still sitting behind a traditional firewall, which also very likely is not cloud native aware. So we'll have a really, really hard time coping with containerized workloads that constantly change IPs all of the time. This is where something like the static egress IP feature can come in, which actually binds volatile containers behind a stable IP, which you can then allow through your traditional firewalls. Stage 3 is typically when you adopt kind of a more microservices architecture. Sometimes stage 3 actually comes as stage 2 if you're very modern and if this comes natural to you. For more traditional enterprises, that's clearly kind of a later stage. Excuse me. This is where things like multi-cluster comes into play, layer 7 observability, layer 7 traffic management, GitOps integration, for example, to do network policy integrations in GitLab, GitHub, as well as advanced security runtime protection that we can offer, advanced scale, advanced churn, and all the way up to multi-cloud use cases. If you want me to focus on any of them in particular, feel free to mention that in the Q&A channel, and I will spend a bit more time on that particular aspect. As we now dive a bit deeper onto the individual aspects, so the scalable and secure networking. Most of you will know us already as a very efficient and scalable CNI. We can run on-prem, we can run cloud, we can run hybrid cloud, so we can run on-prem in, for example, BGP mode, an overlay, VXLAN, leave, whatever. In cloud provider environments, we can natively integrate with the cloud provider SDNs, but then we can also actually not use them because some of them have, for example, limitations in scale, and you will run into IP exhaust issues, so you can go back and actually run an overlay. But then as well, because we can run on all the cloud providers like equally good, we're really good for multi-cloud use cases because we can then, for example, run a multi-cluster scenario across cloud providers or across cloud and on-prem environments. On the level left, we can not only connect parts or services together, we can also provide load balancing, and in a variety of ways. We can replace kube-proxy, so you can achieve a high performance implementation of kube-proxy that can scale really, really well. But then we can do a lot more. We can also become what's called a north-south load balancer, essentially load balancing into your cluster. So you can turn any Linux and in the future Windows machine into a load balancer machine and, for example, replace entire F5 boxes. In the latest version, we can also implement Kubernetes ingress. So we have an implementation of the Kubernetes ingress controller and can thus also do all of the layer 7 load balancing as well, both into the cluster and also between services and across clusters as well. On the security side, first of all, yes, we are a CNI, which means we can do enforcement on the network level, which is actually very, very important and an aspect that should not be underestimated. Even if you're running a high-level concept like a service mesh, you almost need to be aware that, for example, a sidecar proxy or a proxy-based authentication method, which, yes, adds additional security from a mutual authentication perspective, does not prevent you from all the potential leaks that you might see on a network. If a proxy does not support a particular network protocol, it is obviously not able to enforce any rules on that. So in order to have correct network security, you also always need to protect your network level first and then add mutual authentication on top, which is why Cilium combines the two together. So very similar to a service mesh approach which is using MTLS, we're taking the mutual authentication to another level and saying, yes, we are enforcing mutual authentication, but we're not limiting ourselves to TLS, which means we have an identity-based concept, but we can enforce this mutual authentication with identities, not on the TLS level, but actually on something more generically that can support any network protocol, which is amazing because now all of a sudden you can support non-TCP protocols and you can ensure that nothing can bypass your authentication and authorization layer. Obviously, we also support just standard Kubernetes network policy, and then we can go further and look into, for example, DNS-based policies, into API-aware policies, and so on. Besides the segmentation or authentication here, we can also do transparent encryption. We can do this using IPsec or WireGuard. Both of them have pros and cons. IPsec has the pros of being FIPS compliant. WireGuard can be slightly faster if no cryptographic or if no hardware offload for cryptographic operations is available. And then the last bucket here is the expansion. This is actually going beyond the single Kubernetes cluster. As I mentioned, we can do multi-cluster in a completely proxy-free manner, which means you can connect multiple clusters together but not actually introducing either egress or ingress proxies, which means you could preserve your natural organic network performance as well. We can then also integrate into, or we can integrate non-Kubernetes, non-container workloads as well. What does this mean? So as I mentioned, Cilium is not really limited to containers or Kubernetes at all. You can actually run Cilium on any machine that you want and integrate that machine into your mesh or into your Kubernetes cluster. So you can run, let's say, have your existing EC2 fleet of VMs or your bare metal database server. You can run Cilium on them and then have them appear, have these machines appear as workloads, very similar as if they were pods. So they can be reached from pods. You can apply network policy. They can, the external workloads can reach the Kubernetes DNS. They can talk to Kubernetes services and so on. That gives you a lot of flexibility to mesh things together and to get to a zero trust networking concept without actually having to containerize everything. Switching gears a little bit and looking into kind of the network policy, forensics, and compliance use cases. The enforcement part is obviously important, but there is more to this, and it's the visibility side. And we'll actually double click on this lower left window here a bit, because that's very crucial. So keep that in mind for a second while we complete this slide. So yes, we have kind of this identity aware network and runtime visibility layer, which we'll look at. But then we can obviously also do a lot of metrics. We can monitor pretty much everything. Of course, how much are we forwarding? How much are we dropping? We have a TLS parser. So we can, for example, answer questions such as what are the negotiated TLS ciphers that are in play? Has anybody attempted a TLS downgrade attack? What percentage of my traffic leaving the cluster is not TLS encrypted, and so on. And then we have more traditional network tap and port mirroring functionality as well, which you, for example, can use to integrate an IDS, such as Suricata. The nice thing about this network tap IDS insertion part is it's identity aware, so you can actually apply this for a subset of the traffic only. And then there is Splunk and Elasticsearch integration. All of this visibility can obviously be shown using Hubble UI, our own UI, but also be integrated into your existing SIM platform as well. I promised that we will double click on this network and runtime visibility use case a little bit. This is an example of a traditional network flow log, a 5-tuple flow log. And you can see typical network communication, this IP talking to this IP on a particular port, and whether it was rejected or accepted. If we take this a bit further, this is what we provide. And when you look at this new view, you will actually, first of all, kind of question, is this even still a network flow log? Is this even showing the network at all? Because it doesn't look like a traditional network flow log at all, but it actually is. It just provides a lot of additional context and identity information. So if you look closer, we see on the left side, we see the source identity. We see a network namespace or a kind of Kubernetes namespace, a pod name, and then we see the entire process ancestry tree of the workload running. So in this case, it was a container runtime, in this case, Docker-D, which was launching, or which has launched a container. And inside of the container, there's a binary crawler running, which is a Node app, which is running node server.js, which then, for obvious reasons, when you look at this, got compromised and an attacker launched a reverse shell. And then you can see with the arrows, you can see the individual connections. So the Node app actually made connections out to api.twitter.com. We can see the DNS visibility that we have, and also reached out to the Elasticsearch, which is an internal service. And then on the netcat side, we see the NC binary, netcat, which was used by the compromised code to reach out to the URL, which is clearly not a reverse shell, which then obviously received instructions, and netcat was used to launch a bash. And inside of that bash shell, curl was used to now poke around and retrieve information, for example, from Elasticsearch. We can also see that we actually see the layer 7 information as well. So we not only see the connection to Elasticsearch, we can also see that there was a get to /users to /search. So we can even see what type of API call was being made. And funny enough, this view, what we see here, is actually for the same traffic as here. And in this network view, you would obviously never be able to tell whether any attack is ongoing, right? Like no network person would ever claim that you're able to see this type of attack based only on a 5-tuple network flow log. And it becomes so obvious looking at this. I've used an example of a compromised code part here with a reverse shell, but this is actually also incredibly useful if you're figuring out where is the network traffic coming from. Is this the actual workload? Is it an application developer running kube control exec, running a bash and crawling around? Is it Kubernetes network-based health checking, and so on? Is it like what type of network traffic is my Kubernetes control plane doing, and so on? This will work for literally any process on your machine. We briefly mentioned that Cilium can provide authorization not only on the network level, which is here the layer 3, layer 4 for the networking folks under you, but also on the layer 7, and actually, for example, limits that a front-end pod can talk to a back-end pod, but can only do an HTTP get to /public, but for example, not do a post or an update, or not access /private or another URL, for example. This same principle works for protocols like Kafka, Cassandra, Memcached, and a variety of other protocols. So you can, for example, also say my pod can talk to a shared Cassandra database, but it can only do a select on a particular table, but it can never update it. Or you can say my pod can talk to a shared Kafka cluster. It can consume on this topic, but it cannot consume or produce on any topics that other teams are using. The DNS server policy is incredibly interesting for rendering or for modeling services that needs to reach outside of the cluster. I'm using mydomain.io here as an example, but another typical example would be your service reaching out to AWS S3. Cloud provider backed databases are in particular interesting because they're backed by hundreds and hundreds of IPs, which are constantly changing. So how do you model them from a network policy perspective? You clearly want to limit the egress ability of your services, because if the code gets compromised, you want to prevent data exfiltration. And this is where DNS policies come into play. How do you do this if the IPs that the service needs to reach out to are constantly changing? This is where you can write a DNS policy like this and actually say, I want my service to be able to reach out to start.mydomain.io, or it could be mybucket AWS-S3.com or some other domain name, right? What Cilium will then do is actually hook into all of the DNS traffic and proxy that, which means that, first of all, it will not even allow any DNS resolution that does not match this domain or this pattern, which means it will get prevented, it will get rejected on the DNS level. And then if it is allowed, only the allowed set of IPs will actually, or only the returned IPs will be allowed, which means that even though AWS S3 might be backed by 1,000 IPs, only the 4 IPs returned by the DNS will actually be allowed. Obviously, this also prevents any DNS-based data exfiltration attempts as well, because our proxy will kind of decapsulate all DNS requests and not allow to do data exfiltration via DNS, either unless you find some way to actually encode that into the DNS name itself, which is, I guess, possible, but very, very challenging to achieve any reasonable bandwidth. And then you would still have to match the pattern, of course, that you are actually allowing. All right, the last piece here is the Hubble or the observability part. So as I mentioned, this is, I think, probably the most significant part overall. Hubble UI, or Hubble, is the observability layer of Cilium, and it's using eBPF to transparently get observability data, so without requiring any manipulation, modification, recompilation of your applications. So you can deploy Cilium and Hubble, and you will get this observability data for your existing workloads as they are running. You can see an overall kind of overview, what services are running, how are they connected. You can even see all the way into individual layer 7 calls. You can configure this to do layer 3, layer 4 only, or layer 7 as well. And then in the lower section, you can see the live view of what are the individual connections or requests that have been observed. You can obviously filter here. You can, for example, show me only the requests that have been dropped, or show me requests with a latency bigger than this, and so on. All of this data can be viewed live, or you can feed this data into Timescape and actually build a time machine. So Timescape is our ClickHouse-based mechanism to actually store this observability data over time. And then you can go back and say, hey, give me this view but from 2 weeks ago in this particular time frame, and so on. All of this data, so like the Hubble UI that we just looked at, which is obviously also available through CLI and API, as well as all the metrics. So the Prometheus-based metrics, and we can look at them if we have time, as well as our network policy editor, which is able to visualize network policies and to graphically edit policies. All of that can either be done at a cluster level or cluster-wide scope, at a multi-cluster scope, or excuse me, you can also tie this down to, for example, particular namespaces and say a particular team managing a namespace can view these diagrams and dashboards and all of these UI tools, but only for the namespaces they own. And you can tie this to a single sign-on provider, Okta, Active Directory, IAM, whatever you want here to actually inherit existing role information you have, and then configure RBAC rules, very similar to how Kubernetes does RBAC rules as well. The last piece here before we wrap up, GitOps network policy guardrails. So a use case that comes up very, very frequently now is that as teams scale up and use more and more Kubernetes, the desire is there for application teams to inherit part of the responsibility for the fine-grained network policy, but a security team still wanting to preserve some control over the network policies. For example, the network policies within a namespace on what pod should be able to talk to what other pod. The application teams should be able to define these rules on their own, but the application teams on their own should not be allowed to open up new applications to the outside internet or to expose them or to do cross namespace traffic. This is where the guardrails come into play. So you can essentially, as a security team, define a set of guardrail rules. For example, app teams can define within namespace and everything else needs to be approved. And then this implementation, which is available for GitHub and GitLab, will automatically approve PRs with network policies that are within the guardrails, and for everything else, a security team or some other role needs to approve the PR before it can get merged. This is available as well and allows the security team to partially delegate the creation of network policies as well. Obviously, you can still, even with this, use namespace and global policies as well. So even if you have this in place, a security team can, for example, always override network policies at the global scale if you have opened up namespace level policies for your app teams. Scale and performance, as I mentioned, eBPF in the beginning is a highly performance way of doing networking, observability, security, and so on. If you're interested in this, I will not go into super details here, but if you're interested in this topic, feel free to check out the Cilium blog. We have blogged extensively on both performance, comparing Cilium data plane to other CNIs, to service meshes, as well as scalability, how to achieve really big multi-cluster systems, if that is a topic of your interest. And with that, I will leave you with a couple of pointers before we open it up for questions. If you want to learn more about Cilium, if you are interested in this, feel free to check out cilium.io. eBPF.io is the place to go. Obviously, if you want to engage with Cilium, try it out, get started, join the Cilium and eBPF Slack. That's the best way to reach the development team, to participate, to ask questions. And then if you want to run Cilium in an enterprise context, feel free to go to isovalent.com. With that, I think we have several minutes left for questions, if there are any. And if there are no questions, I'm also happy to demo the metrics real quick.
Exactly. So thanks a lot, Thomas. It's fantastic. All of this technology is really, really cool. Actually, we are using it. We are using Cilium already in Apuyo Cloud, which is our latest container service here in Switzerland. So it's opening up many, many different doors and possibilities for our service as well. So it's fantastic to learn more about it. If there are any questions, in the meantime, if you would like to show something else, of course, please feel free to take the stage.
Yeah, actually, I want to make sure we have enough time for questions, but I'm always happy to demo a bunch of fancy metrics as well.
Of course.
Let me see. Let me know once you can see the Grafana dashboard here. I think it should be coming up. So we have a wide variety of metrics that we can show. I'm showing kind of 3 dashboards here. For example, we can see on the network level how much is being forwarded. Here we can see that some network packets are being dropped. Like, oh, that's probably a bad reason or a bad sign. So we can actually go in and see why was it dropped. And we can see that we have a steady flow of network policy or policy-related flows. So that's something that we would then, for example, want to look into Hubble and see which pods are actually subject to this. We can see that we can observe the TCP layer. So we can see that we are constantly missing certain TCP SYN X, which is a clear signal that connections are, for example, timing out. Obviously, this is a demo app that is purposely fully doing this. You can go down there and actually see kind of a lockdown of what are pods that are subject to the policy deny. So we can actually lock this down further. And then go here into the DNS dashboard, which is probably the most favorite dashboard of everybody, because DNS is reason number one for any incident. So we can see, for example, how many DNS responses or how many DNS failures are currently happening and for what reason. And then what pods are subject to DNS errors. So you can immediately see whether your app is subject to DNS errors. We can also see, for example, the top 10 DNS queries. We have an HTTP dashboard here where we can see the number of HTTP requests, the latency of individual requests, and so on. So a ton. That's kind of the high level. But then we can also go out into very detailed, for example, TCP metrics and actually measure the smoothened round trip time, which is incredibly interesting. We see here that from time to time, the Prometheus pod has a very bad smoothened round trip time, which probably indicates that it gets throttled or rate limited. You can go further and actually understand how much traffic individual pods are doing. What is the total traffic pods are doing, right? Which pods are responsible for example, network latencies going up, and so on. And last but not least, we can go really low level and actually all the way look at, for example, network interface statistics. And you can, for example, correlate that to whether certain virtual machines or certain nodes are overloaded. So this is just a very small glimpse at kind of metrics that we can provide. So we can go all the way of kind of high level HTTP, DNS level that you'll use from a service mesh, all the way down into lower levels that you would only expect from a network device type, and correlate all of this information together. And this makes it relatively simple to troubleshoot network issues very, very quickly.
Excellent. Very impressive. Very, very impressive. So I don't see much activity in terms of questions on the chat as well. So I think we are probably arriving at the end of this session. Just a quick reminder before we close this session down. The next editions of our CNC Meetup will be on May the 12th, the next one. There are still slots left, so if you would like to present some technology, some practice that you are using in your own environment, please come and tell us. We would love to learn from you. This community is built by you, so it's very important that you participate. Then we have 2 more sessions this year planned on August 25th and November 24th. So please don't hesitate to let us know if you would like to participate. This video will be available on vision.tv starting tomorrow. So please subscribe and share as well. If you would like to, of course, ask questions, feel free to contact us and to contact as well the speakers of today. And thanks a lot for joining. If you watch this on YouTube, thanks a lot for watching until the end. And first of all, thanks a lot to our speakers, to Moritz, Melissa, and Thomas. It's been a fantastic evening, a really, really interesting session. So thank you so much. And see you next time at the next CNC Computing Meetup Switzerland. Thank you and bye-bye. Bye-bye, Melissa. Bye, Moritz.